think I'll let the
Working. This is what I see right now.
okay, nice. Let me sing the link.
Mhm.
So yeah, so were you
There we go.
We are still waiting for some more. Okay, nice. So we have enough people. Good afternoon, everyone. So welcome to today's UMD Journal Club talk. We are welcoming Dan Sokratov giving us a speech on high magnetic field research in the condensed matter systems. So Dan is a student of Professor Jean-Pierre Paglioni, doing some experimental research in strongly correlated systems. Okay, Dan, take over.
Thanks for the introduction. Hello, everyone. I am Dan. I'm going to be talking about high magnetic field research as introduced. So for a, sorry, getting used to Max. For a quick outline, we're going to talk about why this is interesting, why you should care about high magnetic field research, talk about different magnets that are used, continuous versus pulsed magnets. I'll mention a few of the high magnetic field facilities. I've only been to one of them, so I'm going to kind of focus some of the experimental parts on that one. Then we'll talk about a few examples of what a project might look like, and quantum oscillations. I don't know how familiar you guys are with quantum oscillations, but I'll describe what that is. And then I'll give a brief summary. Okay, so why should you care? Well, first of all, it's neat. Like fundamentally speaking, we should be interested in pursuing physics. And this is one of the ways you can kind of push further and further into different energy aspects, right? It's kind of like why you should keep building bigger colliders. It gives you more phase space that you can explore. So the other thing it allows, because we're getting more phase space exploration, we can have better comparison between theoretical models and what we can achieve experimentally. I'll talk about these numbers later, but currently, like for continuous fields, the limits are right around 45 Tesla. So if you have some theoretical prediction that says, we should be seeing something at 60 Tesla, you can kind of check it with pulsed fields, but you can't really explore it all too well in a continuous manner. There's always potential for new physics. The further you push boundaries, the more you can discover. One of the examples I'm going to show, it's a superconducting material. People thought it would be the potential for interesting physics, blah blah blah. As you push field, so if you guys know a little bit about superconductors, there's a upper critical field. When you push beyond that, the superconductivity just collapses. Interestingly enough, if you go high enough in field along a certain range of angles, superconductivity reemerges. No one predicted that. No one knew why that would be happening, but it was experimentally measured, and then there was theory that could try to explain it. And this is something that we're looking for with facilities like these. And there's applications in different energy sources like tokamaks, for example. In case we tried to do fusion with tokamaks, I don't know how much you believe in that being the future of fusion energy, but it's a possibility for sure. And there's future in other sciences like bio or neuroscience, exploration of how our brain works. We'll certainly have to do something with magnetic measurements. Okay, so just a brief kind of typical range of what magnetic fields you'll be seeing. So just for reference, about 10,000 Gauss is a Tesla. Actually, exactly 10,000 Gauss is a Tesla. So on the range of 10 to the minus 9 to 10 to the minus 8 is kind of what your brain operates on. Way over on the other side is neutron stars, 10 to the 17 Gauss. We exist kind of in this middle range between 2 or 0.2 Tesla, actually above MRI, so like in this range here. Most magnetic fields, so most pulsed fields are somewhere in like 40 to 60 Tesla range. The non-destructive ones can go up to 100 Tesla, and then destructive ones we can push to 2000 Tesla, but that's still nothing close to like what we can see in the universe. Okay, so what kind of magnets are we using? What is the difference? So the big breakdown is continuous versus pulsed magnets in a lot of these facilities. So continuous fields are exactly what they sound like. You can stay there for a prolonged period of time. Of course, that's energy intensive for certain types of magnets, but nonetheless, you can do that. You're forced to stay at like lower fields when you do that, but the fields are still pretty high for useful physics. So really the advantage is exactly time. You can explore phase space in detail. So you can do some angle dependence, or you can try doing pressure on your samples, or strain, or optical measurements, X-ray, whatever. Anything that needs some like, yes.
Angle between what?
Right. So for example, you have, let's say you have a unit cell. Let's say it's tetragonal, right? So you have like AA is the same, in plane is the same, and then there's one plane that's different, right? So for example, I expect that my behavior of material is the same in plane, but if I rotate to out of plane, it should behave differently. It might have like a different response to magnetic field. Maybe I'll see different types of physics in it. So as angle, you can mount your sample such that you're turning it in the magnetic field. Good question. Okay, here's an example of like a complicated phase diagram you can do with continuous fields. So here you have something like, normally you're just doing field, but you can also do angle. You can apply pressure if it's inside of a pressure cell. You can get really detailed studies in these continuous magnets.
Question.
Yes.
What's the usual magnitude for continuous magnetic field?
So in ready systems, like for example, we have in our lab, you can go up to 14 Tesla, which is very good.
14 Tesla?
14 Tesla, yes.
Yeah, so that's still continuous, you're saying?
That is still continuous.
Okay.
When you go to these like high field facilities,
Yeah.
the one I was just at this past week, you can go to 41 Tesla.
Okay.
If you go to hybrid magnets, you can go even higher. I think the current limit is 45 Tesla, which is extremely high. But for a lot of those facilities, you need to it's not, you have to book a specific project and it has to be approved. It's not as easy as you can just show up and measure.
I see. So what happens if you stand in front of that, like 14 Tesla or?
Yeah.
40 Tesla.
So nothing will happen to you unless you have a pacemaker. There's always like safety. There's always like a 10 and 100 Gauss line within which magnetic fields are strong. Next to one of the like really strong magnets, we kind of played around with this. Its 100 Gauss line is like, so okay, I'll kind of have a picture of this later, but there's like these big cells that all these magnets are stored in.
Yep.
Kind of like, imagine this room, but like, I don't know, triple this room, right? That's the cell that this whole magnet is in and you're working in. And then they're kind of arranged next to each other. So next to you is a different cell with a different magnet, et cetera. So this one magnet has such a big field that its 100 Gauss line like goes into the neighboring cell. And you can just take like a fork or some metallic object and just like float it there. You barely hold it and it just like floats in there for you, which is, playing around with magnets, but it's kind of fun.
So your molecules inside your body won't be magnetized.
No, nothing bad will happen to the molecules inside your body. The thing that can happen if you get super close to these magnets, like your credit card can get erased.
Okay.
so that's something to watch out for. But no, nothing dangerous to you unless you have a pacemaker.
Okay.
Yeah. So and like I said, usually in technology, applications usually rely on continuous fields. Like tokamaks, for example, I think you need. Actually, I don't know how big of a field you need for tokamaks, but I think it's a pretty significant field that you try to confine all this plasma with. Okay, so the advantage of pulse fields, on the other hand, is you can reach much, much higher fields, right? Like, so for the continuous fields they have in Los Alamos, for the pulsed field magnet they have in Los Alamos, the non-destructive one, you can reach 100 Tesla, which is more than double the current limit we have for continuous fields. So even though, you get only about 15 milliseconds worth of taking data, it's at much higher fields, and you can still get a lot of data points there. The world record for non-destructive, as I mentioned, is 100 Tesla. For destructive ones, you can reach 1200 Tesla or even higher. There are claims that people have reached 2000 Tesla. Yes.
Ignore me if you're going to go over this, but I'm curious about how like a pulsed field is generated.
I will go over this in a second. Yes.
I see. Quick question from the audience.
Yes.
So the audience asked, is there a way to shield the fields? How to shield the magnetic field?
Shield from what? Sorry.
Yeah, from like leaking out from like a.
You can have magnets if I may.
Yes.
So like our dilution fridge downstairs, it's basically a solenoid, right?
Yeah.
And so you'd put your sample inside of that solenoid.
Yeah.
But there's also an exterior solenoid in which you run a counter-propagating current, which produces a magnetic field in the opposite direction, which then basically by,
I see.
interference outside of there, the magnetic field is greatly diminished.
I see. So Derek is saying that we all have some counter-propagating.
Not all of them do.
Okay.
So that,
Yeah.
only certain magnets have this.
So when you go to like really, really high fields, you can't cancel it exactly, and there will be fields coming out.
Okay.
The point is, all of these figures that I'm citing, that is maximized within a certain bore. Basically, you have a certain range where you actually have your sample, and that's where all of your field is maximized. Yeah, there's random stuff happening outside, but you're not measuring anything that's outside.
I see.
So it doesn't really affect your experiment very much.
I see.
Yeah, and I provided a link. I can send it to anyone interested. It's a 10-second long video. It's of the setup. I think it's a 1200 Tesla. Completely destructive. Like everything blows up in this room. I can't play it now. I didn't put I don't actually know how to put like a video inside of a presentation. So I didn't do that, sorry. All right, so let's talk about continuous magnets really quick. So resistive magnets, like what you know from undergrad classical physics, it's a solenoid, you're running current in the solenoid. There's some resistance, there's gonna be some heating, but inside of the solenoid, you're producing a field. So basically the only difference between resistive magnets and superconducting magnets, and I'll talk about this also, is what kind of material the wire is made out of. For superconducting magnets, it's made out of a superconducting material. And there's an upside that, when you run a current through it, there's no dissipation. So there's no heating issues that you will have. The problem is that in superconductors, there's a upper critical field. So if there's a high enough current, the current itself will create small magnetic fields inside of this wire that will break superconductivity. So then you're back to just a normal metal. In resistive magnets, here's, by the way, what a cell looks like. You can kind of see this line right here. This is the 100 Gauss line for this magnet. The magnet is this thing right here. This is the 100 Gauss line, which is enormous. For normal magnets, it's like inside of the magnet, so you don't even need to have the line. And yeah, 100 Gauss. Let's see, I think Earth's magnetic field is like, it's like 0.5 Gauss, right? So it's like, much, much higher than that. Not that Earth's magnetic field is super crazy big, but nonetheless. Yeah, so this is your magnet. This whole huge thing up there is the probe. That's what you insert inside of the magnet. There's like a liquid helium chamber here to cool everything down, and you have all of your electronics that you're setting up here. In this picture, there's no tank. Whenever they have to refill the liquid helium, they bring this like huge construction crane, I guess, and just like literally lift the whole tank. I don't know if you've seen those tanks. They're like enormous. They're taller than I am.
Quick question.
Yes.
When you're at one of these facilities, like when I go to a radiation facility, we have to wear like a dosimeter to like.
No, you care about nothing.
You have to
No.
worry about like the accumulated
Nope.
magnetic field dose. Okay.
Nope. MagLab is hilarious. It's like the least secure national lab I can imagine. Like the thing our staff scientist there tells me is like, yeah, please don't take other people's data, but outside of that, everything is fine, do whatever. Like they really have nothing about security, not like, Los Alamos does. So pros of resistive magnets, you can sweep fields really quickly. You can just dump a hilarious amount of current in, and as long as you can cool down your system, as long as there's not like external heating, you can just keep pumping the field higher and higher. And that lets you, well, first of all, you save money on liquid helium, which is expensive, especially now with the war. There's very little supply of natural gases and helium including. And I guess that's a pro, but yeah, the magnet can trip, which happened to me, but it won't quench. So with superconducting magnets, sometimes the magnet will freak out and basically will think that it's not cold enough and it'll like shut down all of the current running through it. Then you have to like, cool down, recool down the system, reset up your magnet, all of that. With these resistive magnets, with the really big ones, the issue is that they're super expensive to build. So if there's any like power differences in the city, then the magnet software that's written will like try to shut everything down to keep everything safe and without breaking. So that means you just have to, you can turn it back on immediately. It's just if your system is at really low temperatures, then you have to recool everything again because all the power shuts off.
Quick confirmation. So
yes.
What does the trip quench mean?
Yes. So trip is what I just described, where all the power will turn off and the magnet itself, like you can put all the power back in and the magnet will turn on and things are fine. So it trips by breaking, but it's pretty quick to recover.
Okay.
The quenching is what happens necessarily with superconducting magnets. It doesn't have to happen, but it only happens to superconducting magnets where the magnet itself has to be below a certain temperature for it to be superconducting,
Yeah.
right? Because it's made out of superconducting wire.
Yeah.
If for some reason that temperature like goes above,
Yeah.
the metal is no longer superconducting and your whole magnet basically shuts down and you have to recool the whole system, which is much more difficult than just recooling like the sample chamber.
Okay. Okay.
Yeah, because with these resistive magnets, I'll describe this in 1 second right here, but basically the way you cool down the system is you just run like a ton of water through it. You do water cooling, as opposed to with superconducting magnets, you need to use liquid helium. And normally that's not too big of an issue because, there shouldn't be much heat dissipation in the system anyway, because it's superconducting, right? There's no resistance. But nonetheless, if things go wrong, the superconducting magnet can freak out and then it might take like days to cool it back down versus hours in this case. It consumes a lot of power. As a fun figure, so this mag lab that I was at in Tallahassee uses about 7% of the entire power consumption of the entire city. Not that Tallahassee is huge, but it is nonetheless the capital of Florida. So no, that would be, that would be ridiculous. But it's actually kind of funny, like they see a power, downward spike if everyone were to turn on their kettle at the same time. So like right around 7, 8 p.m. when people try to put on like tea, there's a small dip in power that everyone has. It's really annoying. And there's actually there's cool designs for how they keep these superconducting magnets cooler. I forget exactly what the name of the person that discovered this is. Basically, they thought that instead of just having normal solenoid kind of like discs, you cut these shapes into them to let water run through. And it's way more efficient at cooling down the systems, and it allowed for much higher fields to be reached. Okay, so superconducting magnets, this is a magnet we have in our lab. It's currently broken, but forget about it. And these are all magnets that are much easier to get in a normal lab. The issue is that they won't let you reach higher fields like you'd like at these facilities. This is what a 32 Tesla, which is huge for a superconducting magnet, looks like at MagLab. Super pretty, but it's basically just a solenoid. Same idea, it's just out of a superconducting wire. And like mentioned, their pros is that they consume very low power because you just run some current and it functions. So it's perfect if you want to sit at a high field and just do measurements there, like sit at 20 Tesla and keep doing measurements. Versus for the resistive magnets, the field that you're getting is directly proportional to the power you're shoving through the magnet, right? So the higher field you're sitting, the more power you're consuming. And the way your, project budget works is you get a certain amount of energy that you're allowed to use for however long you stay at MagLab. And so if you run out of that energy, you can go and ask for more, but your experiment ends. The downside is that you will get lower maximum fields and also a lower, slower field sweep rate, because basically if you try to run too much current through your superconducting magnet, once again, you break the actual superconductivity in the wires, and your magnet itself will stop functioning like a good magnet, like you expect it to be. And like mentioned, it can quench, kind of already described what quenching is. Okay, and then the last thing is there are hybrid magnets. Now those are kind of this is 1987, I think, like one of the first hybrid magnets that was built. They're kind of a new thing. Basically, it is what it is. It's a combination of a resistive and a superconducting magnet, kind of like, concentrically placed. I don't know why exactly that lets you reach a higher field, but I think like the superconducting magnet, I think it's just about how much power you can afford to put into your system. And if you optimize it correctly, you can reach higher fields than resistive magnets allow by themselves. So yeah, these are the highest fields you can reach out of continuous magnets. The downsides is basically all of the downsides I've described for both the resistive and the superconducting magnets. It can quench, it eats up a lot of power, you need a ton of cooling. It's like the most annoying one, but it lets you reach the highest fields. So that's the biggest upside. And then let's talk about pulsed field magnets. So the setup here, it's still the same solenoid. The difference is that basically instead of having a constant power supply that you're putting in there, you're storing a bunch of energy and you're dumping all of it over a really short duration through your coil. So you kind of have like a short instance of time when you reach these super high peak fields, like 100 Tesla or 90 Tesla or whatever. And then all of that, gets dissipated and you have to recharge the whole system. So there's ones that, so it can't maintain fields for a high duration. Typically 15 milliseconds, 15 milliseconds is kind of like the limit, but it's typically in the microsecond to millisecond range for these high fields. And so some of them are multi-shots. That means you can recharge on the scale of like hours. Some other ones that are not as like precisely well built, it can take like, maybe 5 hours to recharge the experiment or even a day. So it really is like, you prepare your whole setup, you get this one burst of energy and then you get all of your data and then you sit there and wait for it to recharge again. But it lets you reach very high fields. Okay, let's briefly talk a little bit about facilities. I'm not going to name all of them, but basically for pulsed field facilities, they are all kind of across the world. There's a lot of them in Europe. There's a bunch in China and Japan. There's a few in like Australia. A lot of the really big ones are, the National High Magnetic Field Lab that we have in the United States. But there's a few other like really notable facilities. Here's kind of a quick map that I totally stole from someone else's presentation that shows like actual locations on the world. But yeah, like I was saying, there's kind of a concentrated bunch in Europe. There's concentrated bunch like in the China, Japan area, a few in Korea. And then there's a few magnets that we have in the US. But there's not that many facilities overall, maybe like 30 or 40 in total. And out of those, there's not that many that reach like super high fields. Okay, so let's talk about quick examples of projects. So here was the material that I was describing earlier. So as you can see, this is the phase diagram. So on this axis, you have the field that you're applying. Here is the rotation, and it's kind of weird. So you should think of it as these are like two different axes, right? So this is rotation from B to A, and then the other rotation is from B to C. The crystal has weird symmetry, so it's a little complicated to think about. But either way, so it behaves like a normal superconductor at first. Then you go to higher fields, you have this like reentrant superconductivity phase, which is interesting. It's not common, but nonetheless. So then everything here, everything in white, you might think, okay, well, we're breaking superconductivity with high enough field, things are behaving well. That's what you expect. There's a field polarized phase, which I don't understand a crazy amount, but that's still the normal state, right? Nothing superconducting. Then you go to this like range of magic angles under super high fields, way above the upper critical field. And for some reason, you get reintroduction of superconductivity. Why? No one expected this. Yes.
Good question. Two questions, actually. First question is from the audience.
Yes.
How does the pulse magnet work? Like, why can we generate such a pulse with such strong magnetic field? So basically, the issue comes, the advantage comes from the fact that you don't have to worry about heating very much. So you're dumping, like I was saying, you store a bunch of energy and you're dumping it all through your coils,
which sounds like what you're doing with a resistive magnet, except there you're just continually dumping the energy. With the pulsed magnets, with resistive magnets, you have to keep cooling down the system so it doesn't freak out, and you can keep putting in the field, right? With a pulsed magnet, it's like we don't have the capability to be cooling down a system at 100 Tesla. We can't shove that much energy and continually keep it cooled down. So instead, you basically kind of forget about the heating in your system, and you just dump all of that current in over a very short duration. So for like a super brief instant of time, you get up to those like 100 Tesla, 90 Tesla, whatever fields.
So when the temperature goes up, does the effective magnetic field goes up or go down?
As the temperature goes up, the field, you mean from heating?
Yeah, from heating.
The field will go down, but because it's over such a short period of time, your temperature doesn't really have much time to increase much. Yes.
Is the like energy buildup, is it just like there's like a bunch of capacitors that are discharging?
Yeah, I think capacitors is one of the ways of doing it. There's I think you can also do it with generators. Those are like the two ways that I know that you can do it.
I see. Yeah, and another quick question on your project and on the applications of high magnetic field for physical models. So when we have very strong magnetic fields, what are the main possible types of interactions, like spin interactions or hyperfine interactions, or some other or just for the usual like a Cooper pair formation in the superconductivity, etc. Can you give me some estimate of the scales of Hamiltonians or energies that can contribute to the like during the high magnetic field?
I mean, that depends a crazy amount on your system. Like, for example, BCS model speaking, if you have a superconductor that has a TC of 3 Kelvin, it's a high critical field, upper critical field is going to be whatever, like a few Tesla. If you have a superconductor that's at like, or actually even millitesla, if you have a superconductor, if you have like cuprates that are like hundreds of Kelvin TC, then you expect that energy scale to be much higher. So it really depends on your system a crazy amount. Yes.
With the superconducting material that you were talking about.
Yes.
What is the?
Oh, what is it? This is uranium ditelluride.
Uh-huh.
This is a kind of a big material in my group. I don't do much research on UT2, so I can't talk about in detail about this. But yes.
What is the 2C angle you mentioned?
Yes. So the magic angle is right here. So it's about 20 degrees up to like 40-ish degrees away from the B axis. So going towards the C axis, there's this region where you have a re-entrant superconducting phase.
It's like the angle of the magnet with respect to.
Oh.
Yeah, exactly. Normally, like I think of tetragonal systems, I guess I could draw it, but it won't be on the camera. Yeah, so if you have like, say you have like a, square-shaped sample has, a little bit of a thickness to it. Like for normal tetragonal systems, you have like, you have your A and your A, so anywhere in plane is fine. And then you have your C axis like outside, right? Your C axis points outside. So if you apply field along C, that's what you normally do. But you can also rotate your sample so that you're applying the field along A, and you might get different properties. Yeah. In this material, there's a different symmetry. So like A and B are not identical. Here's another project. This is something I'm more used to. So you have a normal material, there's an effect in materials called quantum oscillations. Basically, it's a result of Landau levels. You guys may have done that in your undergrad or grad E&M courses. Basically, when you have a particle in a magnetic field, it's going to start doing like a helical shape, right? There's quantized energy levels that are accessible. So basically, in a material, when you're sweeping your magnetic field, you will pass your Fermi level like your Landau levels start crossing the Fermi level, and there will be oscillations on your Fermi surface. So there's oscillations in the density of states. If there's oscillations in the density of states, you're going to see that in magnetic susceptibility or auroral resistivity. And sometimes these can be extremely large. And actually from those oscillations, you can determine what the Fermi surface is. It's one of the ways that you can actually like measure a Fermi surface. And generally, you know, there's a Koselich Thouless, is that right? I think there's like I think that's the name, Koselich Thouless model or something.
KT transition or something?
No, I'm not thinking of the transition. Whatever. Either way, there's an equation, and there's like 3 terms in that equation that kind of determine how your oscillations kind of like fall off or like disappear. One of them is temperature. So you know, as you increase the temperature of your sample, the oscillations become smaller until you can't see them at 15 Kelvin. The other way is angle. So if you rotate away from the strong axis, as you rotate away from the strong axis, your oscillations can start disappearing. And another way is called the Dingle temperature, and that's more with like disorder. And that's not really something that you can like continuously change in these samples.
Quick information. So is that like block oscillation or some other oscillations? What's the terminology here?
Yeah, this is Shubnikov de Haas. I'll talk about this later. If you see it in magnetic susceptibility, it's going to be de Haas von Alphen. But it's the same idea. It's it's always related to Landau levels. Yeah, here actually I'm going to talk about quantum oscillations real quick. So you know, particle in a magnetic field, helical shapes, like I was talking about. So basically, you get these quantized energy levels, Landau levels. When they pass the Fermi surface with your varying magnetic field, cause oscillations in the density of states at the Fermi level. That causes, you know, Shubnikov de Haas oscillations, which you can see in resistivity, or de Haas von Alphen oscillations, which is in magnetic fields or in magnetic susceptibility. Sorry, they still result. You know, it results from the same physics. It results from the fact that your density of states is oscillating because you're moving your like quantized energy levels past your Fermi level. So here, this is what like background subtracted data on the top looks like. So, you know, you have some, well, here, you have this resistivity signal, except, you know, something similar on a cantilever for magnetic susceptibility. You subtract your background and you get this thing on top. I don't have a mouse. Okay, that's fine. Oh, I do have a mouse. Yeah, you get these oscillations on top. If you Fourier transform this, you get these nice peaks. If you're me and you Fourier transform this, you get like really broad, really shitty peaks, but that's a different problem. And this is the basic setup. I'm not going to go super deep into this, but you have some piezoresistive material. And basically, what you're doing is you're mounting your sample onto one of the contacts of this piezoresistive material. You're creating a like Wheatstone bridge, if you guys know Wheatstone bridges, just a really good way of like isolating changes within one resistor. Basically, a Wheatstone bridge is constructed in such a way. I think a Wheatstone bridge is like here. It's like this. So it's 4 resistors all in parallel, and there's like a line right across also, I think. Basically, the idea is that if all of these resistors are equal value, then you should get no voltage drop across, no current drop across, one of those. But if one of those resistors is varying, then you will only get resistance values out of that one resistor. And because of the setup, you can do it really, really carefully. That's how you get these really beautiful, really accurate signals from the oscillations.
Yeah, a quick question from the audience again.
Yes.
So, so have you heard of Hofstadter butterfly in?
I have, yes.
Yeah, in the experiment.
So I don't know a crazy amount about Hofstadter butterflies. I have heard about them. For my undergrad, actually, one of the PhD students there, his thesis was on like a possible, like one of his materials kind of behaves like how it has some of the Hofstadter butterfly physics, except in a 3D material. I think generally Hofstadter butterflies are in 2Ds, but his like somehow, you can kind of, yeah, exactly. It's a TI. You can kind of extend it to 3D.
Yeah,
but I know very.
Yeah, what's the typical like magnetic field that causes that kind of butterfly phenomenon?
Oh, I have no idea. Yeah, I really don't know.
Depending on material. Oh, is there like a typical range, like
Well, so
a few Tesla or a few millitesla?
Like usually when you're seeing this, you're measuring quantum Hall effect and you're sweeping both magnetic field and gate voltage. So you're sweeping the magnetic field and the charge carrier density in your system, and you're measuring the differential conductivity.
Okay.
And so then you're usually sweeping between 0 Tesla and like, I don't know, like 9 or 10 Tesla.
9 or 10
because you
Tesla?
have to go
Okay.
higher to see this effect. Yes.
I see. Gotcha. All right. Gotcha.
Cool. And yeah, so this is one of the ways you can map the Fermi surface is with these quantum oscillations. It's one of the very reliable experimental ways. As there might be different ones. I mean, outside of that and ARPES, I don't know if are there any other ways of getting the Fermi surface experimentally? I think normally people just do ARPES and quantum oscillations. I don't know if there's any other ones. If there are, feel free to correct me. So yeah, here's some Fermi surfaces that you can calculate, and then you can compare with results from experiments. So that's one of the good ways that you can kind of go back and forth between theory and experiment on quantum materials. Okay, so to quickly summarize my slides, high magnetic fields facilities are, I think, essential to quantum matter research. It's kind of like, the analog I would give is CERN. And these like high particle accelerator facilities, the higher in field you can go, the more of the phase space you can explore, the more you can learn about your materials and hope for other physics. Depending on what your project tries to get, you have to choose between using pulsed or continuous magnets. Generally, the way these facilities are built, there's like one big project in mind, and generally facilities either have like continuous magnets or pulsed magnets. There are a few that have both, but generally there's like some spatial separation just because of like how much money it takes to construct all these facilities, and the fact that they need different power supplies and different constructions in that regard. And yeah, just to recap, pulsed allows you to have higher fields, but for very short durations. Continuous gives you much longer measurement time that you can spend to do like finer detail analysis. And improving magnet technologies can lead to new discoveries and potentially new types of physics and potentially new applications. So something that we should keep putting money into. Thanks. Any questions?
Yeah, a few more questions.
A few more questions, great.
Yeah, on the kind of physical models, because I as a theorist, I care about more like how the high magnetic field are used, especially in our theoretical models. So suppose we have some hyperfine states.
Okay.
Will the high magnetic fields be useful to detect the hyperfine states or some hyperfine structures?
I am not a nuclear physics expert. I think the fields that we're going to hear are way above what you generally need in those experiments.
Yeah.
I think there you really don't need to go to 40 Tesla. I mean, maybe it depends on what specific compound you're working with, but I think generally you don't need super high fields. I think Zeeman splitting happens at like pretty low fields.
Then let's be more specific. Why do we need to go that high magnetic fields? Like, what kind of new, is there anything new, like especially in physical models, that shows up in high magnetic fields?
Well, normally you wouldn't expect that superconductivity reemerges at 40 Tesla. Right?
Oh, okay.
And here you just measured a sample and it did.
Okay.
So because it does, that means you might have a more complicated way of your a superconducting pairing, or maybe there's some other interaction happening that you wouldn't expect in the system.
I see.
So you can kind of say, okay, this theory maybe doesn't support this behavior at higher fields. So this something else is something we need to go with.
I see. What about something like resistivity or for example, resistivity dependence on temperature in the high magnetic fields. Is there like any new behaviors other than some Jude model or some other?
Yeah. So some materials, the material, for example, I'm working on happens to have what is referred to as like extremely high non-saturating magnetoresistance. So basically, in normal materials, your magnetoresistance is like quadratic up to some point, at which point it like saturates. No matter how much more field you put in, your resistance is not going to change much. In some materials, that it can stay as quadratic, or under different physics, it can even be linear magnetoresistance up to the limits that we can push to. And it's interesting. It's generally speaking, what people attribute that to is some like topological protection for why resistivity can keep rising. There might be like for example, in a lot of Dirac semimetals, this is a behavior that happens extremely high magnetoresistance and it's not saturating. So detecting those things in resistivity can lead you to kind of classifying your materials as such. With regards to temperature dependence, usually a lot of these quantum effects start becoming more and more important at lower temperatures. When you kind of screen out your phonons, you screen out like more dominating temperature scales. But for an example, so I was showing quantum oscillations here, right? In the samples I just measured, actually here. So this is in resistivity, right? So as you can see here at 15 Kelvin, the oscillations are gone. In my samples, I could still see oscillations at 50 Kelvin, which is a huge temperature scale, normal for like experiments. And it's I don't know why, but sometimes these things say maybe how well this interaction happens in your material, or some specific part of the Fermi surface that's determining this property.
I see. So you're saying that even at higher temperatures, which is way above the usual so-called quantum regime, that we can still see the oscillations?
Yes, sometimes in some materials.
I see. That's interesting.
Yeah.
That's good to know.
Yeah, it's really interesting that, and here's the more interesting part. So this material that you have right here is barium aluminum 4. At 15 Kelvin, the oscillations are gone. Yeah. My material is europium aluminum 4, same exact crystal structure, same exact unit cell, has a charge density wave. Oscillations die off at like 50 Kelvin. Why? What is the difference? Like, what is changing? And by same unit cell, I mean like there's less than a 0.5% difference between lattice parameters. Like it's basically the same thing. I mean, yes, europium has magnetism, but like in the strontium case, that does not have magnetism, and it's still true. You still get charge density waves, and you still get oscillations that are, die off at super high temperatures. Why?
So there's no like commonly agreed theories on.
Well, the problem is these Fermi surfaces are really complicated to figure out, I think, and like theoretically compute, you can compute it for some amount of interactions, and then you say, okay, what if we add in spin orbit coupling? Okay, great, you compute it with spin orbit coupling, and then you say, okay, what if it's even more complicated than that? And the more you push the buttons, the more and more difficult it is to calculate out how it's theoretically supposed to behave. Like if you have like a layered material or something, and not only do you have the interaction between this layer and this layer, but also this layer and like that layer, that's very difficult to compute theoretically, right? These materials are brilliant. They kind of just know, electrons know what they're supposed to do, but we struggle computing how that's supposed to interact, right? The more interactions you have, the more difficult it is to understand how it's going to behave.
I see. So far you don't know, like, for example, whether it's the Fermi surface contributes more or electron photon coupling contributes to the difference, or etc.
The problem is you don't like, if you just list off a random material, I think it's pretty difficult to figure out what's going to be dominating its physics.
Okay.
So you can do some brief computations, and then experimentalists are going to look at those computations, be okay, maybe that's interesting. Let's go compute it, or let's go measure it, and then you measure it, and you see something more interesting or less interesting or whatever. And then you kind of do this back and forth where we see maybe this is a direct semi-metal, and they go and they play around with their models, and they go, okay, yeah, actually we got a band crossing, so maybe it is a direct semi-metal. It has this point and blah blah blah.
I see. Gotcha. Yeah. Any more questions?
Great.
All right.
Perfect.
If there are no more questions, let's thank Dan again for this nice talk.
Yes. Thank you. Thanks for having me.
Yeah, we can stop sharing.
Great. I'm gonna let you figure that out. I don't know much. There's hopefully still. It's recorded. It's
Yeah.
there is